Hey, hey. Whoa. That's great. Thank you. Um, well, thank you for being here. Last day in the morning. You're courageous. I have the great pleasure today to present, share the stage with Subro Krishnan and Konstantinos Karanazos, and to present the work done by a lot more people at the Microsoft Cloud Information Services Lab. These are a research group and the big data team of Microsoft. The agenda for today, we will present high-level, sort of what are the workloads that we operate in Microsoft, give you a little bit of background and context. I will summarize briefly the federation architecture so that we're all on the same page. Lots of people probably heard us speak about this in the last few years, but we'll give you some context. And then Kostas will describe the more fun stuff, the advanced policies that we're building on top of it to really shape the traffic within the federation. And Subro will share some more data from our clusters, from our big production deployments. So for context, what is the journey of scheduling at Microsoft? So we started several years ago. Similar to what happened in the Hadoop world, we were building sort of a single framework, right? It was a bit more capable than MapReduce. It was like close to a Hive Tez, if you want, in terms of surface exposed to customers. It was proprietary. It's called Scope. And the idea here that's a little special, a little different is this was a distributed scheduler. So each one of the jobs was independently queuing their request across the cluster. This was by design because we need to scale to very, very large cluster sizes, very, very large jobs. And the thought at the time was that the centralized scheduler couldn't make it. So over time, intuition similar to the development in the Hadoop world. This guy is great, performs fantastically, scale beyond anything you've ever seen, but people want to do other stuff on top of the same hardware. And so the decision was made to leverage Yarn. That was around 2013 or so that we started looking at this, and we decided that Yarn was the right technology, right? There was a big community, lots of expertise, other people deploying. And so we moved towards this world of multi-framework, open source-centric infrastructure. And it turns out to reach our scale, we had to sort of introduce new architectural ideas in Yarn, the notion of federation. Where are we in this journey? Things are looking good. Looks like a curve, a hockey stick, or whatever you want to call it. It's in percentages, so sooner or later we'll stop. But the deployment in production cluster is going very well. We started very slow, experimental, a small number of clusters, small test environments, and then we're really picking up the pace at this point. This slide is based on like data of a month or two ago, so we probably have a few more percent, maybe 80% of the machines have been moved. Now, I cannot give you the details of how many machines, but we're in the hundreds of thousands of nodes fleet-wide, right? So here we are the 80% of hundreds of thousands of nodes. Okay, so we decided to move to Yarn, but the bar is high. Individual clusters are 50,000 nodes and up. We have many of those, but each one of our cluster is actually a very, very large number of machines. The individual jobs, many of the jobs are small, some are medium-sized, and there are some of the guys that are a couple million tasks and several petabytes of input. Okay, so we need to be able to handle those guys as well. Each one of the tasks, as a consequence, there's a very long tail of tasks, but the 50th percentile used to be around, for some of our busier cluster with shorter tasks, we're around 10 seconds, a 50th percentile duration of tasks. And in the process, we are hitting really good marks, pretty close to 60% CPU utilization, fleet-wide average across months, okay? This is really, really hard to achieve. It's very easy to get a few machines to run really hot for a while. Keeping the entire fleet this high up on CPU utilization, I'm not talking slot utilization, CPU utilization, is actually really quite hard to achieve. And in fact, it turns out that this boils down to a ridiculously large number of scheduling decisions per second, right? Our clusters have sustained 40,000 QPS at the scheduler. Now, it doesn't mean we schedule 40,000 different containers per second, but we have to do 40,000 decisions. Some of them will be promotion and demotion of already running containers, but the number of decisions that the scheduler needs to do, it's really, really large. And if you've ever worked on any performance sides of Yarn, you'll know that the capacity schedule is not going to get you there easily, right? So the decision was, well, we can try to push really hard and be the only one that run at this crazy scale, or we federate. And we leverage the good size, maybe a couple thousand, 3,000, 4,000 nodes, individual clusters, and then glue like 20 or so of them to achieve the very large scale. So the bottom line, if you want to get up there, you got to federate. So what does federation mean? You have a very large collection of nodes, and you just partition them into subclusters. Each subcluster will be owned by a single resource manager, of course, running HA, and this looks and feels like a standard Yarn cluster to you. Now, we do not want, however, to partition and ask customers, you can submit here or there. We want to hide all of this behind a single set of interfaces that make it look and feel like a single giant Yarn cluster. To do this, step one, we need sort of some form of central coordination. This is a state store. It's a highly available SQL server in our case. It's hidden behind APIs. You can deploy different HA storage systems, Zookeeper, or whatever else. Each one of the resource manager will be heartbeating periodically and reporting information like membership, number of machines that is being run, general health and state information. We also introduce a bank of routers that sits in front. They are hidden behind a VIP in our case, and they expose the entire set of protocols of the RM and hide the fact that we have multiple RM behind the scene, right? So they will, on behalf of the customer, reach out to multiple RMs, get the information, combine them, and answer them for the customer. And of course, we want the router to be stateless, and so we interact with the state store to maintain some small amount of information needed for router to remain stateless. So now let's look what happened to a job. Let's assume that this little green box is an application submission. This is sent from the customer to the routers. The routers run a set of policies inside them that help them decide which one of the RM should I start the application in. So where's the home, in a sense, of the application? In this example, the RM of subcluster 1 is our home. And at this point, we will do the standard thing that Yarn does. We will pick some node, based on all the scheduling properties that the RM enforces. At some point, we'll have resources for this application. We will pick one of the resource manager. I'm zooming in here. And the request is sent to the NM to start a container. The container is now launching an AM. Here's the other thing that is a little bit different than a standard AM. A normal AM will directly talk with the RM that launch it. Here, we want to hide the fact that you're coming from this RM. There might be others RM you need to talk to. So we have an AM-RM proxy, which is a service running on the node manager, which will basically act like a man in the middle. Every communication between the AM and any of the RMs will go through this proxy. And of course, we enforce this through token mechanics. So a request for container now is going to go from the AM to the AM-RM proxy. The AM-RM proxy has another set of policies that can be run here that, for example, can determine how to split a single request into smaller requests that will go to each one of the RMs, or a subset of the RM. The requests go to the various RM. The RMs will independently make decisions and send back the answers. And for example, the RM2 might have granted the ability to start on this other node manager a task. The task gets started, and now we have communication, standard direct communication between AM and tasks. So if you notice, these allow us to do a couple of things. Control all of the traffic is going to go through either the router or the AM-RM proxy. So we can shape the traffic, right? We can send more or less traffic to each one of the RMs based on policies. It also allows us to have individual jobs spanning multiple subcluster. So when we have some of those very, very large jobs that touch a lot of data that is stored anywhere in the federation, we can really span a single job across multiple subclusters. In principle, using all 50,000 nodes for a single job. So this is kind of just summary and review of the things we've done so far. Here's some of the new stuff that we're working on. We introduced this notion of a global policy generator. This is, in a sense, the guy that will tell everyone else what to do, right? Is going to control policies both at the routers, at the AM-RM proxy, and as we will see from what Costa will present, also will influence the behavior of the RM. So to some extent, will determine the policy for the RAM. The key intuition here is the GPG, or Global Policy Generator. It's sort of an offline component, or it runs online, but you can imagine it as being always outside the critical path of all of the decisions. All of the decisions will be done by the RMs and by the containers, and this component is sort of monitoring and instructing various components of what to do. But the direct resource request will not flow all the way through this central guy. It also leverages both information in the state store, and it publishes decision into the state store so that all of the other components can learn their new policies on Heartbeats through the state store. And this allows us to have an authoritative place where all policies will be stored. So now, let me give you an idea of a couple of set of basic policies. This is stuff we have in production right now. And Kostas will talk about a bit more of the advanced stuff. At the router, the main job of the router is, as we said, routing AMs, right? We do this fundamentally by a weighted random, so we want to kind of cover a little bit, spread around the load across all of the RMs. The main goal is fault avoidance, right? So we want to make sure that the AMs are owned by different RMs. Not all of our AMs are owned by a single RM, as well as there's a bunch of extra internal Microsoft pieces that make sure we try to put them on very healthy nodes. This is because historically the scope AM is not HA. There is a new work, the scope on TES or graphene effort that has been presented earlier this year that with which we are moving scope to leverage TES as the AM control flow, and so we inherit the beauty of TES HA for the AM. So some of these requirements will be a little less pressing going forward. We also have other policies like round robin or priority orders. This could be useful in some of our particular environment. They're also useful for debugging, right? You can easily say, put all the AMs here, so it's very easy for me to pick them up and explore, right? I don't have to hunt around and figure out where the AM, in which subcluster AM is running. The second set of policies is in the EMRM proxy. The goal here is to route resource requests. And we can do sort of split and merge of the request, right? So if you request for 100 containers, we can split it into multiple requests that go to different RMs and combine the results on the way back. How do we do this? We always try to respect subcluster locality. So if you ask to run preferentially on a certain machine, we'll send your request to that subcluster so that you have a shot at getting the exact machine you want. We also try to load balance the different subcluster. So on Heartbeat, the MRM proxy learn the headroom in each one of the subcluster, and so we can route our traffic also based on different loads, as well as we allow the operators to configure weights. The operators might want to say, hey, I want to stress test the infrastructure. I want to put more and more load on one subcluster and see if the RM can keep up. Or you want to say, hey, I need to shut down this subcluster, so let me progressively lower the load onto this subcluster until it's completely empty, so that they can, replace machines or other functionality like this. Also, we're working on, Botang is working on latency mitigation. The idea is if I send my request, some of the RM might be very busy, might be slow at giving me more containers. Some other RMs might be pretty free right now. So we can detect this and sort of extend the notion of delay scheduling we have in Yarn, also cross subcluster by at the MRM proxy by sort of dequeuing from one request from one RM and requeuing in another RM to improve our chances. With this, I conclude sort of the basic policies. If you have questions, we can discuss about them later. And I leave the stage to Kostas.
Hello, everybody. Thank you, Carlo. So Carlo talked to you so far about the federated architecture we use in our clusters, as well as the basic policies that we are using to do the scheduling. Now, I am going to talk to you about, I will discuss some more advanced policies that we have designed and experimented with in order to maintain our hierarchical queue capacities across the whole cluster. So let's take a step back and see what we really want to achieve here. So remember that we have these massive clusters with tens of thousands of machines each. We have a lot of, we have a few tens of subclusters at each of them, and these are our goals. First of all, we want high utilization. So this means that we want as high utilization as possible at every subcluster. At the same time, we want to to have fairness across our users. So it doesn't matter like who gets what at every subcluster, but globally we want to be fair across our users. And the third one is locality. So if someone asks for, has some machine preferences, we want to do our best in order to meet these demands. And in order to do that, actually, we have to do two main steps. The first one is what we call shared determination. So this means, as I said, we have multiple users. Let's say one user takes 20% of the cluster, the other 80% of the cluster. And we really want to say at each subcluster how much each of them will get. The second main task, once we know that this user will get that much at that subcluster, we want to say, OK, I have this, let's say I have 1,000 requests for user A in subcluster 1. How will I assign these tasks to the machines? So which machines I will pick for that user. In order to do these two steps, we consider multiple alternatives. So the simplest one you can think of is a single scheduler for the whole cluster. So we can use, for example, the fair or the capacity scheduler in Yarn across our whole cluster. This would be ideal in terms of our goals. I mean, we can use all the goodness of the mature schedulers we have in Yarn. But on the other hand, it's not a viable solution because it cannot scale to 50,000 nodes or to the 40,000 decisions per second that we have to support in our clusters. A second alternative would be instead to use one scheduler dedicated to every subcluster. That would certainly scale, but it will lead to low-quality scheduling. And to illustrate this, I will show you just a small example. So let's consider this very simple queue hierarchy. We have two users, QA and QB, two queues. Each one should get 50% of the whole cluster. And let's say we have this small cluster with two subclusters, 16 nodes each. And you see the demand. So the user A has demand 12 at every subcluster. The other one has 4 and 12 respectively. Let's see what we can do if we have one scheduler per subcluster. One idea would be to be very strict in terms of fairness, so we don't give more than 50% to every subcluster. So that would mean, based on the demand of every user, that would lead to this situation here. So you can see that the first subcluster is underutilized. So although we are very good in terms of locality and fairness, we don't utilize our cluster properly. A second solution would be this, where we ignore locality completely, and we say, OK, we will give you 50% at every subcluster. This is very good in terms of utilization and fairness, but it's not good in terms of locality, because the user B has taken more containers in subcluster 1, although he has not asked for them. A third solution would be this, where we ignore fairness for a moment, and we deal with locality. We care about locality and utilization. So very good locality and utilization, but you see that the user B has less than 50% that he has probably paid for. So essentially, what we really want to do is to reach a situation like this, where we say that in the first subcluster, it is OK that user B takes only 25%, as long as it takes 75% in the other subcluster. So that is great both for utilization, fairness, and locality, right? How can we do this? This is our proposed solution. So as I said, we have this two-step of shared determination and placement. For the shared determination, we have two new algorithms. The first one runs very often, so every couple of seconds. We call it global instantaneous fair allocation, or GIF. And the other one is an LP-based, which we run every so often in order to perform queue rebalancing. I will talk about these two algorithms in the next slides. And for placement, once we have decided how much each user gets at every subcluster, we simply use one of the existing Yarn schedulers to do the allocations. In our case, we use the capacity scheduler. So let me double-click on the GIF algorithm. This is the architecture that Carlo described before. So we have the two subclusters. Each of them has an RM. So what the algorithm does as a first step, every RM periodically sends some aggregate information about its queues at the global policy generator. So this information can be for every queue of that subcluster, it is the used resources and as well as the demand for new resources. And the GPG, the global policy generator, gathers that information, it aggregates them, so it creates a global view of the cluster. So we know for every user across the whole subcluster how much it uses and how much it needs. And as a second step, we need to determine now, based on this use and demand, we want to determine how many resources each queue will get, each user will get at this subcluster. How do we do that? The first step is that, let's forget for a moment that we have subclusters, given that we have this global view of the cluster. Now we will calculate how many resources each queue should get globally across the whole subcluster. We do that in a proportional manner. We use proportional work-preserving fairness, and for that we are using the preemption calculator that is already in the capacity scheduler. And once we have determined that, okay, this user will get that much of the whole cluster, then we look at its subcluster, and we want to calculate for that specific user how much it will get at every subcluster. We have two main ideas here. The first one is that we do it proportionally to what the user is already using at every subcluster, and we do that in order to minimize preemption. And if we have even more capacity to give to that user, then we do it greedily by assigning it the capacity based on the least loaded subclusters. Once we do that, this is an iterative algorithm that reaches a fixed point, and once we have decided for every user at every subcluster how many resources it should get, then the GPG will send this back with a heartbeat to the RMs so that they know exactly how much they should use at every subcluster for each queue. That was the GIF algorithm. As I told you, we have this LP-based algorithm as well. So what this does is that GIF essentially looks at the instantaneous demand and says how much you should get at every subcluster, but at the same time, periodically, let's say every 1 minute or so, we want to look at historical information so that we rebalance the load across the subclusters. And we are using a linear programming algorithm in order to do that. As I said, it is invoked less frequently than GIF. And the other advantage of this algorithm is that in case one of the subclusters gets disconnected from the GPG, it can still use this information in order to perform the placement locally. In order to compare how well we did, let's say, with compared to the existing approaches, we built a queue hierarchy generator. We are about to open sources, so in the upcoming weeks, we will post a patch about this. What is cool is that it can be used both for federated clusters that we care about, as well as the non-federated that everybody else is using. We generated hundreds of queue hierarchies with different characteristics, different number of subclusters, number of queues, queue complexity, etc. And this is some results that have to do with utilization and fairness. So I have I compare three algorithms here. So we have the KCS is one capacity scheduler per subcluster, and then I have the GIF algorithm and the LP-based algorithm. As you can see, the K capacity schedulers cannot do more than, on average, 85% utilization, while our GIF algorithm can do almost perfect utilization. It reaches, on average, like 98%. And LP is quite good in the 90s. And in terms of fairness, of course, if you have one capacity scheduler per subcluster, you're going to do better. But still, we can see that GIF and LP are also having very low error, so the lower the better here in fairness. And to wrap up about the advanced policies that I presented, as I said, the main idea here is that we are performing placement independently from shared determination. So essentially, we are doing shared determination globally with aggregate information periodically in the GPG, and then we perform the placement with the capacity scheduler at each subcluster. And just to take this idea a bit further, can we really use this in order to improve existing, even non-federated subclusters? So if we take a look at the current YARC schedulers, this is essentially the loops that they are going over. So we have for each queue, for each application, for each resource request in that application, we check if we can place on that node. So essentially, as you can see inside the loop, we have the shared determination and the placement. And we do them each time, like we try to perform shared determination for each placement. Is that really needed? Do we need to perform shared determination at each placement decision, or can we decouple this instead and say, okay, every few seconds I will say how much user will be getting, how many resources, and then I do the placement based on that decision. And with that, I give the stage to Subru that will discuss. Yes. The hierarchy is the same, but the demand, like how much you are allowed to use at every subcluster is not anymore. So think of the figure that I saw in the beginning that you can have 50-50, like the two queues, but then in one subcluster you have 75-25. So that's what the algorithm essentially changes, right? The queue hierarchy is the same, yes, exactly, yes.
Need not be. Need not be. Need not be. Is it? Yeah, but it's not a hard constraint, like because like Costas talked about, we have the rebalancing which happens more periodically offline, and if it does need to, it can come up with something. But yeah, so far it's been fine. Thanks, Costas. So yeah, Costas talked about all the algorithms which we're doing. So now let's talk about where the rubber meets the road, right? So how has our production experience been post the migration, right? So first, this is going back to what Carlo talked about, right? What is the challenge? So this is actual data from FIRE for production clusters. So C1 to C5, they are about 30,000 to 50,000 nodes. So we have tiny clusters which are 30,000 nodes essentially. So and looking at it, so we have data input from few MB to few petabytes. We have job runtime which runs from anything from seconds to days. And we have jobs with tasks which are having tens of tasks to millions of tasks, right? So, and our workload is predominantly been batch processing. But as you can see, we are also slowly, so like, for example, C1 has about 35% of other workloads already in place, right? So the workload is also slowly, the pattern is varying. What does this entail for the scheduler itself, resource management itself, is how many scheduling decisions we have to make per second. So as you can see, we are going anywhere between 10,000 to 40,000 is the scheduling decisions per second which our scheduler needs to handle. And if you guys notice, C4, why is C4 hanging around at 1,000? So when this is the actual data we got from production, we looked at it and said, okay, why is C4 looking like it's like 2,000 scheduling decisions per second? And we realized that we actually have a problem in our metrics reporting. So the C4 is also pretty close to C5. While we have to take care of so many scheduling decisions per second, we need to make sure that we do this with a very good latency, right? Because we are also churning through billions of containers a day. So if you look at even our 99 percentile, for the most part, is within 10 seconds. So this, we need to now shift. So what we have is we have shifted from a distributed scheduler, existing distributed scheduler to Yarn, and while maintaining these characteristics. And one of the other key factors is our utilization of the cluster is when you have clusters which are tens of thousands of nodes and you have multiple of them, utilization is very important because just the COGS are hundreds of millions of dollars a year, right? So, and we are pushing our utilization to 60% on an average, and this is how we are migrated. So July is when it was running the legacy distributed scheduler. And by Feb, we are like, as Carlos said, we are close to 80% where we're running Yarn, right? So as you can see, this is the box plot of how the utilization has been. We have maintained the close to 60% utilization, while the good thing is we have reduced the variance, right? So if the 25% boxes and the 99 percentile has come down. So that means we're maintaining the utilization while reducing the variance. Another way to look at this is how are the nodes actually processing the tasks, right? So in this graph, each dot is a node in our cluster, right? And how many tasks is it processing daily? So if you see in the legacy system, there's a wide range from 0 to 35,000, right? So it's a huge range. While in Yarn, while we move to Yarn, we have kind of clustered nicely around the 15,000. So 15,000 plus or minus a couple of thousand, right? So nodes are a lot more balanced once we move to Yarn. So and at the same time, what to understand is, to looking at the x-axis, the data, every day, it happens to all of us, right? Our clusters, the data slowly keeps increasing, the amount of data we are processing. So we have done this while the average data being processed by the task has slightly increased, right? Another way to look at it is, let's look at how the tasks are performing now. So the dotted line is the legacy system, the blue line is the yarn. So as you can see, the data is slowly increasing. This the top left graph, the intuition is how much data each percentage of task is processing. So if you're a little bit if you're below, that means you're processing more data, right? So when you move to yarn, the data keeps growing. But the important thing is, while the data keeps growing, the execution time has not. We have actually brought it down. Little bit, I'll come back to the job runtime. So we've brought down the task execution time. Now, a better way to look at it is how efficiently are the tasks performing, which is how much data is it consuming per second. As you can see, we're doing much better than the legacy system. Actually, to be clear, in a very tiny task, because we have like in the earlier slides we described, we have a task which ranges from pretty small to pretty big. In the tiny tasks, we're doing slightly worse, but the really gigantic big ones, as it gets bigger, we're doing better. And our postulation is because we have the overhead of the centralized scheduling, whereas distributed scheduling is directly queuing, etc. For the really tiny tasks, that doesn't get amortized well. Yeah. No, this, yeah. This,
How do you read that? You have tasks ranging from,
so,
tasks may range from 1 KB all the way to 10 gigs per task. Sorry?
yeah, it is. This graph actually keeps going a little further. So the graph does keep going a little further, but
But the task have a timeout of 6 hours, I think. So there is a bound of how much you can process, right? So look at roughly the megabyte per second, up to 6 hours, they're roughly the limit. I've seen them, I run tasks around up to close to a terabyte per task, and then running out of time past that.
yeah.
But depends on the computation.
So finally, so task performance is good because we want to individually look at it, but overall what matters for the user is how is the job performing, right? So we have successfully managed to migrate to a centralized scheduler in Yarn, while the median, so the job runtime, the blue line is talking about the job runtime, the median is 0.96, so it's pretty similar. And like again, we talked about the jobs which are pretty small, we are slightly taking longer, but as the job size gets bigger and bigger, we are doing much better. Looking at the total computation time, right? So there we are actually doing, because we're processing a lot more data. Even though the job runtime, we have maintained the previous job runtime and haven't even improved it for the larger jobs, we are doing a lot more processing. And that's, again, organically, clusters are always, I guess it's the same for all of you guys. Your clusters are going to process more. So that's the, in summary, what it shows is like, so we have this federated architecture which does allow us to scale Yarn to 40,000 nodes, 50,000 nodes, and to handle the scheduling decisions rate, which is the 40K QPS. An even more fun, challenging thing was the federated architecture, what it allowed us, because like Carlo pointed out, it's transparent to the application, which is very important because when you have such large cluster sizes, when you upgrade them, it has to be an in-place upgrade. You cannot say, okay, I have 50,000 nodes, now I want to upgrade them to a completely new architecture, so let's bring another 50,000 nodes and then just swap, right? So this, because of the transparent nature of the architecture, this did importantly allowed us to do an in-place migration. This has already been more than hundreds of thousands of nodes has already been migrated. I guess there's nothing more to add. So we have some time for questions. 5 minutes exact to be.
So I have a question. So in these subclusters, the hardware is homogeneous or it's like?
No. So I'll just, this actually, okay. So Sunil's question is, are the hardware homogeneous? It's not, because especially when you have large clusters, you have multiple generations of hardware. In this graph, something which I didn't call out, which is the shades are what are the generations of hardware. So if you have black, the newer, but we don't recall off the mind what.
The darker are bigger.
Yeah.
The
Yeah.
darker nodes are bigger, beefier machines.
The newer generations. So
And
if you
also
have, you can see the shades, so you have multiple generations of hardware.
And we try to put in each subcluster roughly the same mix of these machines. We had the episode in which our policy that was doing this was not quite working correctly, so some cluster had much lower, like more of the older machines where in some of the subcluster we get like higher queuing there, and there's been a little bit of issues. But in general, the hardware is heterogeneous. Federation does not assume that the cluster is all same size. In practice, as you deploy, that's probably a reasonable way for you to stay sane on roughly having the same things happening in all cluster. But one of the things you can also do is specialize each one of the cluster. You can have a subcluster is only GPUs, right? Or a subcluster that is small and have really, really fast heartbeats, right? So that you can do fast interactive queries there. So the architecture allows you to play around with all of that, and the policies allow you to take advantage of the diversity as well.
So another interesting thing to look out here is because we have a centralized view now, if you look at it, the older hardware, which is lighter shades, are actually processing less tasks now, on an average per node. So as you get black, darker, you're processing 15 to 20,000, and you are here within 10,000 and 5,000. Whereas there, even the older hardware, which was struggling, was going up to 30,000, because you're distributed scheduling without a centralized view of the heterogeneity, etc.
So you have a node labeling possibilities? Are you labeling the nodes, or?
No.
There's no labeling per se. The only difference is that we advertise different amount of capacity for every one of the machine types.
Yeah. Node labels is something which the folks here are looking at, but it's not there yet in this, because this is actual production data. So node label is still in the pre-prod and evaluation stage. No.
I think you're right. It's definitely non-trivial. I think it's the same class of problem of locality, right? So you can build resolvers in a similar spirit in which I resolve a machine to a subcluster. I can resolve labels to a certain amount of resources in each one of the subclusters, our intuition was as we built policies was from the beginning, we're not going to know what we will need. So we made the policy mechanics very easy to change and very easy to push from the center. So you can update stuff in the state store and push down new behaviors to the different nodes, because we know we will not get it right at first, right? And scenarios like the one you describe, or live sites that sometimes happen, we need to deal with it. We don't know what's happening, and we can just push new policies much faster than doing a redeployment. A redeployment, one of these clusters might take a couple of weeks, right? Because just the size, and we need to go slow. We need to make sure that the rolling out works well. So we need a faster mechanism to change policies. That's why we build a lot of mechanics in Federation to do policy pushing.
Yeah, no XML files. To be put it in another word.
Does this mean the older hardware, because it's an average daily task, right?
Yeah.
Yeah.
Before the older hardware was actually churning through a lot of tasks.
Yes.
Does it mean that there's still a lot of room here? Because it's only finishing like 10,000 tasks, right?
No,
It's more that this
the
balance,
load
right?
on the cluster is very comparable, right? The load on this cluster is very comparable. We're
It's
just
just that this
spreading
thing
it
got
differently.
Fast and you have more.
Yeah.
So the second question is, sure, you're not buying 50,000 more machines, but when you migrated from the older system to the new system,
Yeah.
you've been doing it at a cluster level, right? You take 2,000 of
Subcluster.
at client. It's per client.
Yeah.
You can think of it like that.
Actually,
The migrating machines is per subcluster, yes.
Yeah. So essentially think of it.
3,000, 4,000 update to the system.
Yeah, queues. Essentially
Yeah,
based on the queues, right?
but not necessarily one subcluster at a time, right? So the cluster might have whatever 10 subclusters, which have 1,000 node each, and then we're gonna add 50 node, 50 node, 50 node, 50 node, and then we're gonna add we get to a point in which we say, okay, now let's add one more subcluster and start populating that one. So those are separate decisions. How many machines you move, and do you move them all to the same subcluster or add new subcluster? That's orthogonal.
You're just moving the workload from old.
We move them per client. So every client.
Yeah, it's queue and users.
And so we have some of the other analysis we've seen also in which you see the fact that we were moving younger, like lower tier customers first. And so you were getting into a situation in which the load on the two, even if you were moving theoretically the same amount of machines, the behavior were quite different because the population, the applications were different, right?
So we're out of time, but we are available. So for offline discussions, please feel free to reach out. Thank you, guys.
Thank you.